Hi everyone, today I have brought a question from the topic of EM waves. So the question says, the electric field in an electromagnetic wave is given by this equation. 2 E naught I cap. I cap here means electric field is along x-axis, isn't it? So at this instant and at this position, z is the coordinate of the point where you are calculating the electric field. So at z coordinate at time t, the electric field is along x-axis. That is what this I cap represents. The question is to find magnetic field at that instant and at that coordinate. So what is the magnetic field? Now, sometimes students do this in this way. They say that peak value of magnetic field and electric field are related by this formula. V naught equals to E naught by C. So the peak value of magnetic field in this question, here this is the peak value, right? The maximum value at a given time, at a given position will be 2 E naught. So this E naught should be replaced by 2 E naught, because in this question the peak value is 2 E naught, isn't it? So they think that the magnetic field should have this much peak value, and they know that since here z is there, it means the direction of propagation of the wave is along z axis, right? So the electric field must be along y axis. Now positive y or negative y, well, that is given by E cap cross B cap should give you the direction of propagation, which I can write as C cap. So now in this problem, the direction of propagation is Z axis, which is K cap, and electric field is along I cap. So what should be B cap? What cross what will give you K? You know this rule, right? So if you go this way, I cross J will be K, J cross K will be I, K cross I will be J. And if you go opposite, you will get negative sign, with negative sign. So here I want K cap, so B must be J cap. So the unit vector of magnetic field should be J cap, and then they think that in the properties of EM waves, in NCERT text, they have mentioned that the phase of electric field and magnetic field are same. So if electric field has phase sine kx minus omega t, where phase is kx minus omega t, then magnetic field also will have same phase, kx minus omega t. So they think, since the phase will be same, these two functions will be same. And this is what they will think is the answer. So this is what few students, or maybe most students, think will be the answer. Now the problem with this answer is, this, if you look carefully, is not a traveling wave. In traveling wave, the function should be, electric field should be some peak value and some unit vector with cos or sine kz plus minus omega t. This is how traveling wave looks like. But here the time part and the position part, the space part, is separated. And when this happens, it is actually, if you see your class 11 notes on standing waves, you will see that whenever space part and time part are separated this way, then it is actually a standing wave. And for a standing wave, the phase of electric field and magnetic field are not same at a given position at a given time, and therefore this is actually wrong. Then how to solve it? Well, then we have to go with laws. So in physics, whenever you have doubt, you have to always go to the basic fundamental laws. Now, which law connects electric field with magnetic field in EM waves? Well, we can use Faraday's law, isn't it? Now, this is the equation that we have to use to solve this question. and this equation is basically Faraday's law. Now, those who have studied Faraday's law as given in NCERT textbook, you may think, Arey, how this is Faraday's law? We have never seen this form of Faraday's law. So that I'll try to show you little bit later, because in exams anyways you don't get time to do derivations and then use the formula. So when they give you E and they ask you B, this is the formula that you need to remember. So what this formula says is, if you take differentiation of electric field with respect to the Z coordinate. Now why Z coordinate? Because here this is given Z. That means these standing waves was formed by two traveling waves in opposite direction, that we know from first view, right? So those traveling waves were traveling along Z axis. If one was going along positive Z, other will be going along negative Z. So if this is given Z in the exam or in the question, then you have to use that Z here. And remember, the differentiation of E should be with respect to the position coordinate, which is Z. And for magnetic field, it should be differentiation with respect to time. Okay. And here electric field is along X. So this is actually EX, and this is magnetic field is along Y. However, we know that already. So let me try to remove these symbols. And remember, this del is called partial derivative. Partial, that simply means that when you take differentiation with respect to Z coordinate, the time coordinate should be taken as constant. Similarly, this is partial differentiation with respect to time. That means when you take differentiation with respect to time, here you have to consider Z to be constant. Okay, so that you have to remember. So here Z should be treated as constant, and here time should be treated as constant. So let's do the differentiation. So if you take differentiation of this E with respect to Z, then 2 E naught will be constant. Don't write IK because this is just magnitude. And differentiation of cos kx will be what? Minus sine kz, and chain rule will give you 1 k. Right? And time is constant, so cos omega t will stay as it is. And that will be equal to minus del b by del t. So now I want b, so cross multiply and then integrate. So if you cross multiply, you will get del b is equals to minus, this minus minus will actually cancel. So I can remove the minus, cross multiply 2 E naught k sine kz and cos omega t del t, right? So now we integrate both sides. So integral of db will give you b 2 E naught k sine kz, and if you do integral of cos omega t, you will get sine omega t by omega, isn't it? And what is this k divided by omega? K divided by omega is what? Well, omega is 2 pi frequency, k is 2 pi divided by lambda, 2 pi cancel, and you all know from school days actually that frequency times wavelength is speed of the wave. Here the wave is light, so speed of the light is c. So k by omega is 1 by c. So it will be 2 E naught by c sine kz sine omega t. And if you want to write in vector form, then you have to just put j cap, isn't it? Because magnetic field was along y axis. So this is the answer. Okay. Now let me try to explain how this is Faraday's law. So you know that Faraday's law is actually given by the EMF induced in a closed loop is equals to minus of rate of change of magnetic flux with respect to time. And obviously the magnetic flux should be passing through the same loop, right? And this EMF is basically work done to carry a unit positive charge around the loop. So this is the work done and divide by the charge. Now this force on a moving charge can be due to electric field or it can be due to magnetic field. However, we are going to apply this law to a imaginary loop for deriving this formula, because this is for electromagnetic waves in free space, in vacuum. So there are no real currents and charges in that free space. So therefore, that imaginary loop, since it is imaginary, it can't have velocity, right? You can't have velocity of nothing. So therefore, this term will not be there. Obviously, electric field can exist, isn't it? So if I substitute this force here, you will get integral E dot dl around a loop, that's why we have drawn this circle, is minus d phi b by dt. So the q gets cancelled obviously. So you can see that the rate of change of magnetic flux is related to the electric field by this formula. Now we will apply this formula in the case of a wave which is traveling along z-axis, and you know electric field in our problem was along x-axis and magnetic field was along y-axis. Okay. Now let me imagine one loop in this free space here. Okay, so this is a very small loop, very small loop. Okay. However, while drawing, I cannot draw very small, otherwise it won't be very clear, right? So I'm going to apply this law to this loop. Now here at this coordinate, electric field is here this way, Ex, and when you go to a different point, electric field is changing with z coordinate. So electric field will change, right? Since we know electric field is along x-axis, let me just remove this x. Okay, it makes the symbols simpler to see. So here electric field is E. When you go this side with Z, electric field is changing. So here it is E plus dE. Now at that moment, the magnetic field everywhere can be assumed to be same, because I am taking a very small loop. And since magnetic field is here, while calculating the flux, I want area vector to be here. That means I am going to circulate this loop this way. Okay, that will keep all my signs correct. So if area vector you choose here, then you have to circulate this way while doing this integration, because this integration is done along the loop, right? So let us start. So when I do integration from here to here, what will this dot product give me? dl is along the loop, electric field is also this side, so this dot product will give me E plus dE times the length of this part, and that length you can see is dx, right? Because this part is parallel to x-axis. This is your x-axis, isn't it? And this is your y-axis, correct? So this dot product I completed for this part of the loop. Then for this part of the loop, dl is along the loop, electric field is here, so they are perpendicular, so dot product will be 0. And in the third part of the loop, dl is down, electric field is up, so dot product will give you minus, right? Cos 180 is minus. Magnitude of electric field is E, and this length is magnitude is dx. And again for the last, the bottom part here, dl is along the loop, electric field is here, so perpendicular, dot product will be 0. And that will give me rate of change of magnetic flux passing through this surface at a given moment. Now since this area is very small, I can write magnetic flux as the magnetic field By, everywhere I am assuming same at that moment, remember, into area. And what is this area? This side is dx and this side is dz, right? So area is dx times dz. So now E dx will cancel with minus E dx. I am left with dE times dx. That will be equals to, this area is fixed, so I can take dx dz outside. I am left with dB by dt. I lose not dE, sorry, I lose dx, and therefore if I bring dz this side, I'll get dE by dz is equals to minus dB by dt. So this is how we can write the differential form of Faraday's law. Now I did this derivation in a very simple way, and in physics, the more you make it simpler, chances are the more you may deviate from the exact method. But I still hope you felt the gist of this equation from this derivation. Now what if in exam they gave you magnetic field and they asked you electric field? The reverse of that. In that case, again, this is not a traveling wave, so you cannot do the same method that we apply for board exams. So here we have to use the modified form of Ampere's circuital law. So which says the integral of B dot dl around a closed loop is mu naught times the real current plus the displacement current. However, we will apply this law for a loop in free space, and in that free space there won't be any real currents, right? So we will get integral of B dot dl is equals to mu naught, and what is the formula for displacement current? Epsilon naught d phi e by dt. Now if you repeat whatever I did in the previous case, I made a loop and I did the line integral of electric field, right, in the previous case. So now you have to do line integral of magnetic field. So if you repeat that, you will get a similar formula, and that will be del B by del Z is equals to mu naught epsilon naught del E by del T. Okay, so whatever B they have given, first you do differentiation with respect to Z, then you cross multiply, then you do integration to find E, and that I will give you as homework. Okay.